Recall that I am to provide you with a solution for exercise 1.3, subpart 3, that the Euclidean distance in Rn is a metric. But before that, a few words. We have just covered open balls, open sets, and why open balls are open sets, with just the notion of a set, any arbitrary set, and the notion of a distance function, any distance function that satisfies the four properties of a metric, without specifying the precise composition of the set or the distance map. To be able to do so, to be able to explore and develop ideas in an abstract setting while still making progress and arriving at results, as we have, is a gift of mathematics, a powerful methodological gift. Jettison the inessentials and work efficiently with a small kernel of ideas and primitives to arrive at big results. But now let's return to our solution. Let F, G, and H be 3 points in Rn, and I'm going to demonstrate that D7 satisfies the triangle inequality and leave the straightforward checks of positive semi-definiteness, identity of indiscernibles, and symmetry to you. Oftentimes in analysis, when we are to prove an equation or an inequality, the strategy is to begin with the square of one side of the equation or inequality and find conveniently that the terms cancel, collapse, or coalesce into the square of the other side of the inequality. And then we take the square root of both sides to arrive at our result. This is one such case. So we begin with the square of the distance from F to G as per the definition in the hypothesis. Now, if we add and subtract HI to the argument of the sum and regroup, we haven't violated the equal to sign. And we carry out the square and distribute over the sums. We have this expression here. Let's now take a small detour. Recall the Cauchy-Schwarz inequality for complex numbers. The square of the absolute value of the sums of the mixed conjugate products is less than or equal to the product of the sums of the individual AI and BI mod absolute value squared. Let's take square root of both sides to arrive at this line. And now, if we constrain AIs and BIs to be real numbers, anticipating the components of F, G, and H, which we can because real numbers are complex numbers with the imaginary part 0, then we can dispense with the conjugate bar over BI and the absolute value signs on the right-hand side to arrive at this line here. Now, if a number, absolute value of a number is less than or equal to the right-hand side, then the number itself is less than or equal to the right-hand side. Why? Well, the removal of absolute value symbols keeps a number the same or makes it smaller if that number happened to be negative. So armed with this result now, let's return to our solution. If we take Fi minus Hi to be Ai and Hi minus Gi to be Bi, then the expression in orange here is precisely the left-hand side of the Cauchy-Schwarz inequality. Can we replace the left-hand side of the Cauchy-Schwarz here with the right-hand side? Yes, we can, provided we change the equal to sign to a less than equal to. And we have now gone ahead and replaced the left-hand side of the Cauchy-Schwarz with the right-hand side. Now observe that the terms in orange are precisely the distances from F to H and from H to G. Let's write that compactly. So we have the square of the distance from F to H and twice the product of the distance from F to H and H to G plus the square of the distance from H to G. Now these three terms here are precisely the square of a sum, which we can write compactly as D7FH plus D7HG quantity squared. And now we can take the square root of both sides, honoring the fact that we have less than equal to here to arrive at this final line. The distance from F to G is less than or equal to the sum of the distances from F to H and H to G, which is precisely the triangle inequality. Observe that H in this line can be F or G or neither. Voila.